Hello, my name is Andy Schweitzer, and this is a quick little video on how to set up and draw a voltaic cell. The voltaic cell that I'm going to look at drawing is a real simple one. It is going to be a reaction between, let's say, copper and silver. So the reaction we've written as AgNO3 plus copper metal yields into 0, no charge. Yields copper nitrate NO3 2, and then the silver is now metallic, no charge. This is a redox reaction. You'll see charges are changing. These are the oxidation states. +2, +5, -1, and then nothing here. So if I were to do this chemical reaction, the half reactions would be this: Ag plus goes to Ag metal. The copper would be no charge going to copper +2. This would be my oxidation reaction, and this would be my reduction reaction. This would happen twice, therefore making this 2, 2, and 2. For my overall net ionic equation would be 2 Ag pluses plus a copper metal yields 2 Ag no charge plus copper 2 plus ion. To know if it's going to run, you would grab your voltages, and I will do that quickly here. Looking for reduction of silver ion is right here at a plus 0.8 volts. Alright, this is going to be a plus 0.8 volts, and then the oxidation of copper is going to be on the chart, but it'll be reversed, and it's right here, so it'd be a negative 0.34 volts because this is the reduction. It's the reverse of what actually I have on my half reaction. So it's going to be a negative 0.34 volts. To get your overall voltage for this chemical reaction, I would need to add these together for a positive 0.46 volts. Okay. Now, if I were to draw out how this reaction takes place, I'm not even getting to a cell yet, but I would simply take a beaker or some sort of thing that can hold liquid, and inside here I would fill it full of my solution. This is my before picture. I would have silver ions in here, my nitrate ions are floating around separately, and they are the spectator ions. This guy is not taking part in the exchange. Simply the silver is exchanging with the copper. Drop in a copper stick, sometimes referred to as a post, and on this thing, simultaneously, two silvers come up and grab electrons. They form solid silver around the outside of this thing. Alright, so this is going to be Ag solid, and then because of the ratios which they combine, it takes two silvers to make up for the one copper jumping off to form copper 2 plus ion. This will happen spontaneously. You just plug it in, and you need a surface by which these two things can react. If the copper wasn't a solid, you do need a solid surface by which to chemically react. In that case, if I just need a surface, let's say I'm going to react gases together, so none of them are solids, we need a surface. We need a surface that's not going to interact. Platinum is an excellent surface which reactions can take place on. Stainless steel can also sometimes work, but platinum is the one we really want to concentrate on. So this reaction, again, it runs spontaneously. Now, how can we take this thing and make it so that we can utilize this exchange of electrons to create something that would run electrons through a wire, and therefore we could do useful things with those moving electrons? And that is where I will draw this voltaic cell. Now again, a voltaic cell is pretty old, going right back to Benjamin Franklin throwing things together, trying to create little ways of storing electricity. But a battery would be a series of voltaic or galvanic cells. This is just a really crude example of just one of them. So, and there are a lot of ways you can set this up, oodles of ways you can set this up. But the simplest way we'll show would be with a beaker, two beakers, each of these containing half of the reaction. And then the exchange would happen over the course of a wire. So my reaction is, with our notation, is going to be copper metal going to copper 2 plus, and then the other half of the cell is the silver plus going to silver metal. So in this case, I would have a post of silver, and I would have a post of copper, and inside the solution I would have copper 2 plus ions floating around, and then over here I would have a solution of silver ions. Hook the two together with a wire. Again, the exchange is going to happen across a wire rather than right on the actual surface. Now at this point nothing will actually occur because well, I guess maybe a very small amount, as a copper metal jumps off, forming a copper 2 plus ions, the electrons are going to flow in this direction. So that's an important electron flow. Okay. In this half I have copper metal going to copper 2 plus 2 electrons. This is called oxidation. You should just realize that oxidation takes place at what's called the anode, the negative source. And I spelt that wrong. Anode. Alright, oxidation takes place at the anode. This is called the anode. Okay. Now, as electrons flow here, this side becomes negative, and again, electrons won't flow towards a negative. But for sake of just finishing this part of the description, as electrons come here, and again, it's not one electron. Basically, one electron would bump another one and then would kick all of them over, and the next one would fall off. So it's kind of like a domino effect. As electrons are here, and it would need two electrons. Two electrons come over here, and then two silvers sense that negative, and they go on to coat this thing with solid silver. Okay. But again, as electrons flow here, we can't have one side negative, one side positive. So we need one more critical piece of material here, and this is what's called a salt bridge. Okay. I'll explain the salt bridge in a moment, but in this case, this reaction is silver plus ions, two of them, going to silver metal, and this will require two electrons. This is called reduction, and the reduction takes place at the cathode. So, in this case, this is everything that we pretty much want to know about this cell. Get a little more room here. About this thing here, you should note a few things: that over the course of this reaction, this concentration should be increasing. So the concentration of the copper 2 plus should be increasing. The concentration of the silver ions is going to be going down. Conversely, the mass of the silver post should be going up, whereas the mass of the copper post should be going down. Electrons will flow in this direction. Originally, when Ben Franklin was actually looking at these things, he and many others kind of thought the positives were moving. So if you think the positives are moving, then you wouldn't even know negatives are there, much less anything else. It would appear as though it's traveling in the opposite direction. And that still is labeled miscorrectly today, and they call it current. Okay, current is flowing in the opposite direction of electron flow. Okay, but that's a bunch of stuff here. Now let's take a moment here and let's isolate why we need a salt bridge or something to balance the charge between the two. So as I blow up a picture of my salt bridge, is in a beaker, and you can pretty much just follow the path of the negative. In this case, I have a post, okay, and electrons are flowing in this direction. So as electrons flow in this direction, I have positives and I have negatives in here. So as negatives enter this thing, electrons will take the path of least resistance. That's why they don't travel through the water and up through this salt bridge and over here. So the salt bridge literally is just a wadding of probably some paper here that fluid can pass through. And it's just a salt that contains lots of positives and negatives. You want a salt that's not going to interact with any of the stuff that has involved here. A very common salt would be something that's not acidic, not oxidation or reductive potential. And they can't undergo oxidation reactions very easily, and they don't precipitate. Therefore, sodium nitrate is a pretty common salt to have in there. Well, as the negatives approach this side, the negatives will start to repel each other, and the negatives will start to push up. And the positives of the salt bridge will attempt to come back down. So the negatives will start working their way this way and come out this way. Again, as we lose negatives are re-entering the solution from the salt bridge, and positives would then attempt to go the other way. So this is only means or reason why we need this salt bridge is to make sure the charge between these two are balanced. Okay, cannot have one side be negative, one side positive, even though electrons are flowing towards one side. Okay, pretty much everything we have here, we've calculated the voltage, which is 0.46 volts. Off the top of my head, I can't think of anything else I'd want to label on this picture. There are lots of other ways of setting up these things. The biggest thing is how you get the salt bridge to work. A very common example is called a Daniell cell. A Daniell cell is just someone who came up with a different way of constructing it. And obviously inside of a dry cell battery and other things of that nature, it's just how you end up exchanging electrons. But a Daniell cell would be like this, where you have a larger beaker and then a clay pot beaker in the middle. Now this clay pot would be a porous clay pot, and you have one post right here and another post right here. Alright, and then make it a little bit bigger. And then in this case, the electrons can go in and out of that clay pot as needed. As electrons are traveling, let's just say hypothetically in this direction, and the negatives would exit this way and positives could enter, and keep the two sides very much balanced electrically. And that is it. Thank you.